I'd like to talk about the thermocouple psychrometer a little bit more. I brought one in for everyone to see. So, I recall from last time, all of these psychrometric methods work similarly. First, you take a sample and seal it up in a small space. And I promised to bring this in today, so I'll show you what I mean by a small space. Imagine this had a top on it. That's the size of the space. I'll pass this around so you can see. This little space. So you take a small sample and put it in here. And for this one, you just push it like this and seal it up. So now that little volume is sealed off, but it's got a thermocouple in the top. And it's got your sample in it. Okay, so you seal it up and you let things come into equilibrium. In other words, let the water potential of the air become equal to the water potential of the sample. When that happens, or even before that happens, the water potential of the air is proportional to the vapor pressure of the air divided by the saturation vapor pressure, which is the relative humidity on a 0 to 1 scale, where 100% is fully saturated, 0 is bone dry. Okay. Now, water is allowed to evaporate from this thermocouple junction. However it gets there, let's not worry about it. That's how the different psychrometers work, is how you get that liquid on this junction to start evaporating. That is not important. Water is allowed to evaporate from this junction. The rate of evaporation depends on the relative humidity of the air in that chamber. The rate of evaporation determines the temperature of this thermocouple. And the output from the thermocouple is proportional to its temperature. So what we have now is a device that gives us an output that's proportional to the relative humidity in the air, which is related to the water potential of the air, which is the same as the water potential of our sample. So, if we have a calibration curve that relates the output from our device, let's say in microvolts, to the water potential, then we can put our unknown sample in here, seal it all up, read the output, and tell what the water potential is. That's how psychrometric methods work. Actually, that's how a thermocouple psychrometer works. There are other ways of doing this, and the one that's becoming increasingly common is to not use a thermocouple, but to put a tiny mirror in that space, and then reflect light off the mirror to a detector, and then you cool the mirror off by using the Peltier effect, right? And cool that mirror off until you reach the dew point. When you get to the dew point, water condenses on the mirror and it doesn't reflect the light anymore, so your detector can tell when that happens. And then you know what the dew point temperature is. If you have the temperature of the air and the dew point temperature, that can also be related to the relative humidity of the air in the chamber. And so these so-called chilled mirrors are becoming increasingly common way to measure water potential in instruments that measure water potential instead of using a thermocouple. And here's a nice, I came across this morning, a nice paper that discusses these relationships between dew point temperature, relative humidity, and vapor pressure. So that's this one. Okay? Easy enough? I'll pass this around. This is a sample chamber that you can still buy actually from Westcor. And it has a little volume in it. There are different sizes of these things. I didn't bring them, but they make different size chambers that fit into this space. This is the typical one. You can see it, and I didn't bring the tool to take this off to see the thermocouple, but if I had, we could remove the top of this. You'd see a little tiny thermocouple in there. It's kind of delicate and easy to break, so that's why I don't like to play with it too much. But you'll notice this is a big block of aluminum surrounding this little tiny space, and that's to keep temperatures constant through that space and eliminate gradients in temperature. Remember these wet junction depressions, I think I've got it on the slide, are very, very small, less than 1/10 of a degree C over the range of water potentials that we're interested in. And so we need to make very precise measurements of temperature. So we have to eliminate thermal gradients. Here are some filter paper discs that are used to make this calibration curve. After all, how do we have something that we know the water potential of? Well, my blue marker, we use the Van 't Hoff relationship. So here's the temperature, the gas constant, the concentration of whatever our solution is. And we can make up a series of solutions that we know the water potential of. And then we can dip a piece of filter paper in one of those solutions, seal it up in the chamber, and then we've got something that we know the water potential, and we can use that to make our calibration. Okay, so here, I don't know, it's just filter paper, right? It's not very color. It's pieces of filter paper. Okay, so that's how cyclometers are. Remember, there were different types of, I had this last time too, different types of cyclometers. They mostly vary in the way that the water or solution droplet gets placed on the thermocouple junction. You can do it manually using pure water. You can do it manually using droplets of known solution. This is the isopiastic technique, which tends to be very accurate for reasons I'll get into in a little bit. And the most common type is the spanner type cyclometer, which is what this thing is. And that just uses a Peltier effect to cool off that thermocouple junction until it's below the dew point. Water condenses on the outside of it. Then you turn off the cooling current and allow that water to evaporate. This is the most common commercially available type. Okay, so that's it. Let me talk about some precautions that we need to take. Okay. Here's this little sample chamber. Okay, precautions. The first one is that the rate of evaporation of water from that thermocouple junction depends on the nature of the geometry around that thermocouple junction. You know, where the wet spots are, the drier spots inside that volume. And so that geometry it's good to have that geometry the same for your sample as for your calibration standards. And that's why leaf discs are often used in a thermocouple psychrometer, because they approximate that filter paper disc that you use to make your calibration occur. So the geometry should be the same. Now, for the isopiastic technique, when you're putting a known solution on the thermocouple junction, and you're looking for the solution that gives you no output from your device, it's always, that avoids this geometrical consideration, because no water is evaporating anyway. And so that's the point you're looking for. I've never used this isopiastic technique myself, but I've often wondered, you're looking for no output from your machine. How do you know that you've got no output versus something's broken? You forgot to plug it in or something, and I'm getting no output. I don't know how that works, but you get the idea. Right? Okay, so the geometrical considerations may be important, although somewhat minor importance. A little bit bigger issue is that these leaf samples, after all, leaves are made to resist water loss unless the stomata are open. One of the environmental conditions that closes stomata is being in the dark. Another one is high CO2 concentrations. Both of those factors tend to close the stomata. When the stomata are closed, the leaf is very good at resisting, it's very good at not losing a lot of water. And so inside this chamber, we're waiting for things to equilibrate. And that, to equilibrate between the sample and the air, water's got to be lost from that sample. When the stomata are closed, it takes a longer time for that equilibration to occur. During that long equilibration time, things can happen, especially in a living piece of leaf. Solutes can be broken down, like large molecules can be broken down into smaller molecules. That affects the osmotic potential. Smaller molecules could be combined into a larger molecule, also affecting the water potential. If you would have living tissue or tissue from a meristematic region, those cells are capable of expanding. Maybe they'll continue to grow and change their water potential. All of these changes in water potential in the cells of the sample are problematic, especially with long equilibration times. So there's nothing can be done about that. It's just that it's good to use as short of an equilibration time as possible. And the only way you can tell that is by playing around with the machine and getting a feel for how long you have to wait. That's another reason for having a very small air volume in the sample chamber, so that you minimize the equilibration time. Okay. In extreme cases, the sample can absorb water that it's evaporated from the junction. It's not so much a problem with the spanner type psychrometer, because that water ultimately came from the air in the sample anyway, and it's just going back to where it came. But, it might be a problem. And again, the isopiastic technique avoids this issue. Again, so far, these three, okay, let me get to the fourth one before I summarize. Another problem, especially with living tissue, or with living tissue, is living tissue is respiring. Respiration gives off heat. Heat, this changes the temperature and makes temperature gradients in the system. And so, for very accurate measurements, you can correct for that heat of respiration on the water potentials that you measure. So here's a couple of papers from mid-60s that show that. You might not think there's a lot of heat coming off from a little leaf disc, and you're right, there's not. But remember, these wet junction depressions are less than 1/10 of a degree C. oftentimes over the range that we're trying to measure. And so even a little bit of a temperature difference or temperature gradient can affect the measurement that you're making. And so for very accurate measurements, sometimes you'll see people correcting that for the heat of respiration. No, maybe that's the last one. Yeah, that's the last one. Okay, so these four, okay, they're kind of esoteric considerations, right? And my point is that they have relatively minor effects on water potential. The thing that has the major effect on making a good measurement of water potential is loss of water from your sample in between the time you excise it from the plant and the time you reach equilibrium in the chamber. So we know there's a one-to-one relationship between water content and water potential. So what's this? This is for a soil. This is for a leaf. And so any loss in water content is going to affect the water potential. So if I take a punch and punch a disc out of a leaf here, and I walk over to the end of the hall and put that disc in my psychrometer, that little piece of leaf has lost water during the whole time I'm walking down the hall. And when it loses water, it changes its water potential. One-to-one relationship between water content and water potential. This is by far the biggest effect on water potentials and the biggest concern that you have to, if you're using a psychrometric technique to measure water potential, this is a big concern. It's a problem. And it's not an easily solved problem, particularly if you're trying to make measurements on plants out in the field on a hot summer day. I challenge you to take a sample from a leaf on a hot summer day and bring that into the lab where your psychrometer is without losing any water. Not easy. Okay? So this is by far the biggest consideration, water loss. And we'll see that in some other techniques too.
How do you avoid that?
How do you avoid it? Bring the plant to the psychrometer one way. It's tough. Take your leaf disc and put it in a space that's very humid. So it may be a little vial with some moist filter paper in it, or take a piece of plastic and take a leaf punch, put it there, fold it in the plastic, you know, so it doesn't evaporate much water. It's a technique like that. You know, it's difficult. Difficult. Yeah. So, but anyway, it's not impossible, and these changes can be minimized. And so it's possible to use a psychrometer to get a water potential. It's not too much of a problem. And psychrometers are used all the time to measure water potentials. Okay? So, we can use a psychrometer like this to determine the total water potential of a sample from excised tissue. We can also use it to determine water potentials of soil samples. So they make bigger chambers and even bigger than that one, big chambers with big spaces that you can put a nice sample of soil in and work the same way. Seal it off, let it equilibrate, measure the water potential of a soil sample that way. Westcor also has, see how old these are, these things break. Westcor also has little sensors like this. This sensor has the thermocouple inside this little ceramic cup. And so the idea is you bury this in the soil and let it equilibrate wherever you want to measure the water potential in the soil. And then with the end sticking out, then you come with this machine, connect it, and make a water potential measurement of a sensor in situ. So this works the same way, except that instead of having the thermocouple inside that block of aluminum, you've got it inside this ceramic cup. And the ceramic allows water vapor to go back and forth. It allows it to equilibrate. You have to put it in place long before you want to make your measurement so that it does equilibrate. But once it's equilibrated, you make your measurement just like any other.
Which would you rather use?
For what?
Like, which method would be your method of choice if you had to go do it?
To measure soil water potential?
Sure. Yeah.
So, my job title, not that defines me, but my job title is crop environmental physiology.
Okay.
So I'm supposed to be working on how the environment influences physiology and physiological things for crop plants, right? Although I don't limit myself to that. As such, I want to go out in the field and measure the plants right out there in the environment that they're experiencing, rather than in a greenhouse or growth chamber or something like that. If I were interested in looking at, say, water use by plants in drying soil, I would use something like this to measure water potential in the soil, rather than taking a soil sample, bringing it in the lab, sealing it up in a chamber, and making a measurement there. I'd put this out in the field. And actually, Westcor doesn't sell this thing anymore, but they do sell data loggers that will read their probes. And you could set up a system where you had a series of these at various depths in the soil, connected to a data logger, and monitor water potentials continuously out in the field. And I think that's an approach.
If you know the water potential in the soil, can you relate it to the plants or not?
Sure. I mean, the pre-dawn water potential of the plant is a good indication of the water potential in the soil over the root, averaged over the rooting volume. So yeah, that relates fairly directly.
Really cannot see the curve during the day, can you?
Typically, I wouldn't expect to see much change with it. I wouldn't expect as much of a change in the soil water potential over 24 hours as in the plant. The plant water potential changes a lot, or can change a lot during the day. The soil water potential is set by the soil water content, right? So here's a graph. Here's the gravimetric water content of the soil. Here's the water potential. Soil water content changes more gradually. You know, you can argue that at times, especially with a dry soil surface, it doesn't change very much at all during a day. I mean, sure, over 4, 5, 6, 7 days, it will change. But during a day, it doesn't change very much. And it's relating the soil water potential to the plant water potential. That's a vague question to ask. I mean, you need more information. I would need more information. For example, the water potential in the plant varies from the root to the stem to the leaf in the bottom of the canopy to the leaf in the top of the canopy. So where in the plant? are you trying to relate those water potentials? I mean, that's a question. The water potential in the leaf depends on the water content of those cells in the leaf. And so when the stomata are open, okay, so at night, when the stomata are closed, no problem, because things come into equilibrium and the water content of the cells is more or less, it doesn't change very much at night. But during the day, when the stomata open and water evaporates from the leaf to the atmosphere, because remember, the water potential of the air is very, very negative. So when the stomata open, water vapor diffuses from inside the leaf out very quickly. That changes the water content of the cells in the leaf, which changes their water potential. And so those leaf cells have a wide range of water potentials that's kind of determined by the environmental conditions of the day. What's the temperature? What's the vapor pressure of the air around the leaves? And so it becomes, to relate soil water potentials and plant water potentials, you have to consider a lot of other things that are going on simultaneously. And, these types of measurements take long enough so that even if I was to measure a lot of leaf water potentials, by the time you finish measuring one, those environmental conditions have changed already. And so the next leaf you measure is going to have experienced different conditions than the first one, and so on. And so a lot of or sometimes to deal with that, people use models of the system. So you model the soil, plant, atmosphere continuum, and the micrometeorology of that system in order to say something about the moment-to-moment variations of the parameters in the system. Yeah, so, I mean, it's a great question, but it's not an easy one to address. So, anyway, here, let's pass this around. You can see this little thing. Okay, so I got past this slide. Okay, so leaf discs or soils. We can take a soil sample, we can stick that sensor in the soil. We can also do osmotic potentials, measure osmotic potentials in leaf cells. For example, one way to do that is similar to the calibration here. You take a leaf and freeze it quickly, like dip liquid nitrogen, or what we used to do is put it between two slabs of dry ice. That was easier for us to get than liquid nitrogen. And freeze it quickly. And what happens is the water in the cells freezes and it breaks all the membranes around the cells. It ruptures the plasma membrane surrounding the cells. So now the pressure potential, once you thaw that tissue out, the pressure potential is zero. There's nothing holding, that force pushing against the water. It just moves. So the pressure potential goes to zero. And so if you take a pair of pliers or something, squeeze that leaf sample, you can get a droplet of stuff out of there, put it on your piece of filter paper, and put that in the psychrometer and measure the water potential of that. And that's the osmotic potential of the stuff that was inside the cells. And that's really a very, very common way of measuring osmotic potentials that people have of plant cells. There's a problem with it, though. What's the problem? What's the problem? You know the problem already, if you think about it. The osmotic potential of the stuff inside the cell is very negative because it's a concentrated solution. But not all the water in the leaf is inside a cell. There's a lot of water in the apoplast, right? In the cell walls and in the xylem. The osmotic potential of that water is close to zero. When you freeze the tissue and thaw it out and squeeze out your sample of your droplet to measure the water potential, you're mixing those two pools of water. And if you're interested in the water potential inside the living mesophyll cells, which typically is what the measurement's being made for, you have to correct for the dilution of that by the water in the apoplast. You get it? I mean, the apoplastic fraction, okay, the proportion of water in the apoplast in the leaf can be appreciable. It can range, here's a table of apoplastic fraction, beta, 5% up to 40% of the water in the leaf is in the apoplast. So that has an osmotic potential close to zero. In order to get at the osmotic potential in the symplast, we make a measurement of the osmotic potential of the stuff we squeezed out and divide that by 1 minus beta, where beta is the apoplastic fraction, the proportion of water in the apoplast. So you see if this is 5%, well, it's not much of a correction. But if beta is 0.4, you divide by 0.6, that makes a big difference in the osmotic potential that you've determined. And so this apoplastic correction, which many people ignore when they measure osmotic potentials, can be a source of error in determining osmotic potentials of living mesophyll cells. Okay. The question then immediately arises, how do you know what this thing is? How do you know the apoplastic fraction of your cell? How do you know how much water is in the apoplast versus the symplast? So,
Would it be proportional? Would it be proportional?
To what?
Like, if you know the species, would it be proportional to like in the cells versus apoplastic?
well, I mean, this table, yeah, is sort of hints at that. Wheat leaves 0.3, eucalyptus 0.4. I don't know how
Accurate.
accurate that is, or how much that
That would
varies.
at least reduce some kind of error, right?
Yeah, there are other ways to determine what this is. And I'll talk about one when we discuss pressure volume. Okay, so this, I don't know if you noticed, but this graph, so here's the